All right, let's take a look at checkpoint 15. So this module is all about improper integration. So that can mean a couple of different things. So we're going to talk about both those cases with this first question here. So part A, so this interval that we're integrating over is infinitely wide. So it goes from negative infinity to zero. So this is one of those cases where we call the integral improper because the length of the interval is not finite. So because of that, we have to set this integral up using a limit. So I'm going to do that now. So for A, I'm going to say the limit as t goes to negative infinity of the integral from t to zero. And I'll set this up so it's a little more friendly for power rule. So 3 minus x to the power of negative 1/2. So aside from that limit, we can handle this integral in a lot of the same ways that we have before. So we're going to carry that limit operator with us for a while. So what is the antiderivative of 3 minus x to the negative 1/2? I'm going to kind of I'm going to avoid using just setting up like a formal integration. Actually, I'm not. Let's set that up. So if I say that u is equal to 3 minus x, that means du is equal to what? Negative dx, right? Now let's not go too fast. So du dx would be equal to negative 1, which means that du is equal to negative dx. So then what does the rest of this integral look like? That just reminded me that I left off a dx here. So let's put that back. So now what does the rest of this integral look like? We should also transform the limits. This is why I don't like doing this with improper integrals. So let's deal with the zero first. If x is equal to 0, then what's u is gonna be equal to 3. I think this t still remains. Because if I have actually, let me think about that. If x is equal to t, so t is going to go to some really, really negative number, and I'm going to subtract that from 3. I think this is now going towards positive t or negative t. Or I'm going to look at it this way. Now t is going towards positive infinity. So a lot of different ways to look at this. I'm going to still say that t is going to, or still the lower limit of this thing is t, except now t is going to positive infinity because I've now um, subtracted the variable. All right, so now what's the rest of this integral look like? Instead of 3 minus x, it's going to be u to the negative 1/2. And instead of the dx, it's going to be negative du. So minus u to the negative 1/2 du. So now we're ready to take the antiderivative. So the limit as t approaches infinity of, all right, now we can use the power rule. So if we add 1 to that, we get negative u to the 1/2 over 1/2 evaluated from t to 3. And now that we've done the u substitution and we've dealt with the limits, we don't ever have to go back to looking at this in terms of x. So now we can evaluate this at the limits. So the limit as t goes to infinity of negative 3 to the 1/2. Actually, let's do one more step before I evaluate this like this. And I have plenty of room here. The limit as t goes to infinity of -2 radical u, evaluated from t to 3. Now let's actually evaluate those limits. So the limit as t goes to infinity of -2 radical 3 minus negative, so +2 radical t. All right, so what's going to happen to this as t goes to infinity? So -2 radical 3 is a finite number. But what's going to happen to this 2 radical t as t goes to infinity? This is going to increase with no bound. This is going to diverge. So integral A diverges. So I said in the setup for the problem here that one of the integrals diverges, the other one converges. So that tells you that if we did this right, then the other one should converge. So I also said at the outset here that there are two different kinds of integrals that we call improper. One is where I basically said there was infinite length because the interval that you're integrating over is infinitely long. This one I don't know if it was described in some of the other videos that I posted, but I call this like infinite height. And the reason I call it that is because this function 1 over radical 4 minus x, it's not even defined over the entire interval that I'm integrating over. So specifically at the endpoint x equals 4, if you plug in 4 for x, this function is not defined. But that doesn't necessarily mean that the integral doesn't exist. And I'll show you, and we've seen lots of examples in that in the videos, and I'm sure in the homework, including this one. So let's go ahead and find this integral. So again, let's set it up. So integral from 0 to 4, and we'll kind of set this up again for power rule. 4 minus x to the, no, -1/2. This time I'm going to actually, because I did the formal setup of u substitution last time, I'm going to kind of shortcut it this time. So I know that I can use the power rule here. The one thing I got to be careful of is that the derivative of the inside function here is -1. So I'm going to want to divide by -1. I know I'm going to have to flip the sign here. So this antiderivative is going to be 4 minus x to the 1/2 over 1/2. And like I said, I also want to flip the sign on that. And I'm going to evaluate that from 4, or 0 to 4. So all told, that comes out to be -2 times the square root of 4 minus x, positive square root 4 minus x. So I need to silence my phone. And that's evaluated from 0 to 4. So, like I said before I started this function, before I integrated it, is not defined from 0 to 4, but the antiderivative is. Which means that even though the function, if you were to graph it out and look at the area underneath the curve from 0 to 4, it would be infinitely tall. It would have infinite height at the right end at x equals 4. But even though the area approaches infinite height as you go towards x equals 4, the area converges. And we're going to see that now. So after I evaluate this at both ends, so -2 times a radical 4 minus 4 minus -2 times radical 4 minus 0. This becomes 0 minus -4. This comes out to be 4. That area comes out to be 4. So one of the areas, sorry, one of the integrals diverges. This other integral converges to 4. All right, so moving on to question 2. So this one, this setup is, I think it was the most recent checkpoint. I give you this exact same setup. I'm asking the same or different questions this time. So again, population of skunks. I gave you the rate of change of the population of skunks on the Pecos campus. I'm asking you how many skunks will be born in the next 20 years. So this is a question. It's not the same question as I asked you last week, but it's a very similar setup. So to answer this question, I can set it up this way. I want to know how many skunks are going to be born in the next 20 years. So from 2023 to 2043. So reference time is 2023. So I'm going to integrate from 0 to 20 of this function here. 300 e to the negative 0.01 t dt. So what is that antiderivative? And just looking ahead to part B, I'm going to be taking the antiderivative of the same function both times. So I want to, after I take this antiderivative, I want to make sure that I keep sight of that. So what is the antiderivative here? And even if you have this from last week, you can still use it. So the antiderivative of this is going to be, remember when you take the derivative of an exponential function, specifically a function with e in it, you're going to multiply by the derivative of the exponent. So when we're going to do an antiderivative, we're going to divide by that. So this is going to be 300 e to the negative 0.01 t divided by negative 0.01. And we're going to evaluate that from 0 to 20. So what is 300 divided by 0.01? Let's not leave anything to chance. So 30,000. So negative 30,000 e to the negative 0.01 t evaluated from 0 to 20. All right, so I really only have to evaluate that at 20. So 0.01 times 20. Raise e to that. All right, 20 times 0.01 negative, so that's negative 0.2. I raise e to that power and I get 0.819 about. And then I multiply that by 30,000, negative 30,000. And I get negative 24,561. Then I'm going to add that to 30,000. All right, so here's what I get, and I have to round to a whole number because I'm talking about living things. It doesn't make sense to divide those up into decimals. So I get 5,438. So this is how many skunks are going to be born in 20 years. So this is part A. So now let's think about what part B is asking me. Part B, how many total skunks will be born from now until the end of time? So how do I set up that? So for part A, I'm asking about a finite period of time. But for part B, I'm asking about an infinite period of time. I'm not asking about an end. So the integral I'm setting up here is this, the integral from 0 to infinity of 300 e to the negative 0.01 t dt. So basically, I'm asking for an improper integral. Basically, what's going to happen to the skunk population or to the number of skunk births as time passes for a very long time. So this is going to involve a limit. So the limit as t goes to infinity, this integral good news is I can use the same antiderivative. So the limit as t goes to infinity of negative 30,000 e to the negative 0.01 t. I should not be using t. That is a bad move. Let's use b. Never use the same symbol to do two different jobs. So from 0 to b. Okay, so what does this come out to be? Negative 30,000 e to the negative 0.01b minus negative 30,000. That's it. Okay, so what happens here? Oh, I left off something super important. I'm going to squeeze it in here. The limit as b goes to infinity. So it's 30,000, that's settled. But what's going to happen to this other term here? What's going to happen as b goes to infinity? It might be easier to think about that if we rewrite this. So the limit as b goes to infinity of negative 30,000 over e to the positive 0.01b plus 30,000. As b goes to infinity, the exponent down here is going to get very, very, very large. So basically what's going to happen is I'm going to be dividing this constant negative 30,000 by numbers that are growing larger and larger and larger without any bounding. So basically what's going to happen is this left term is going to go to 0, and this 30,000 is not going to change. So this is just going to be 30,000. And now that I'm saying this, I expected these to be a lot closer together. So I want to go back and look at part A again. So I am sure about the 30,000. When I plug in 20, let's just work it through one more time. So 0.01 times 20. So e to the negative 0.02 is 0.818. If I multiply that by 30,000, negative 30,000, I get negative 24. Yeah, okay. Never mind. Okay, I feel better about it. Okay, so in 20 years, I'll have 5,000 or so skunks. But if I let this go out to the end of time, I'll have 30,000 skunks. Okay. All right, so I feel good about question 2. And then question 3. So I have a particle moving in a straight line, and I'm giving you its velocity function. So the first thing I'm asking you is to find this integral. So the integral from 0 to infinity of that function. So let's do that. So first, I will set it up as a limit because I'm dealing with an infinitely long interval. So the integral from I broke my rule again. Just use b. I don't want the same symbol to be doing 2 different jobs. So the limit from b to as b goes to infinity of this integral from 0 to b of 800 over 2t plus 1 to the third dt. Let's set up a u substitution. I think it's a good move for this one. U equals, what's a good u? So we have parentheses. That's usually a good thing to look for when you're setting up a u substitution. Inside the parentheses is this expression, u equals 2t plus 1. Du dt should be 2. So du equals 2 dt, which means dt should be equal to du over 2. All right, does that help me? Actually, let's deal with the limits too. If t equals 0, then u should be equal to 2, 0 plus 1, or 1. And if t equals b, then u should be equal to 2b plus 1. Okay, so I think that helps me rewrite this whole integral. So the limit as b approaches infinity, that becomes this. The integral from 1 to 2b plus 1 of 800 over u cubed times dt, which is du over 2. I'll simplify a couple things here. One will take me a little more convincing. It'll probably take me a little more convincing than the other. 800 over 2 is 400, right? I'm going to go ahead and simplify that. Hopefully that you'll take. The other one, I might have to talk you into a little more. B is going to infinity, right? So basically, I'm going to let B take on larger and larger and larger and larger values. Does it really matter if I double those larger values and add 1 to them? No, I'm just going to keep this B. It's still going to do the same job that I want it to. I'm still letting it take on very, very large values. It doesn't really matter if I'm letting it go to large values or double some large value plus 1. It's still going to do the job I want. I'm still exploring what happens as those numbers go way very far to the right. Okay, so I have a good integral here. I think we're in a good place to actually find this antiderivative. So what is this antiderivative? We can use the power rule. In fact, why don't I just do that now? Set it up for the power rule. 400 u to the negative 3 du. So this becomes the limit as b approaches infinity of 400 u to the negative 2 over negative 2. Evaluated from 1 to b. So I can simplify again. I get negative 200 over u squared. And just like I do way too often, I left off this limit operator. Negative 200 over u squared. Evaluated from 1 to b. So now let's plug in those limits. So the limit as b goes to infinity of what? Negative 200 over b squared minus negative 200 over 1 squared. So now we're in a place where we can think about what happens when b gets really large. So when b gets really large, we have a negative 200, a constant number, being divided by a very large number squared. So what's going to happen when you divide a constant by a number that's getting very, very large and also being squared, so becoming even larger? This is going to trend toward 0. So this limit is going to trend toward, well, this first term is going to trend toward 0. This second term is a constant 200. So this gives me 200. So the value of this integral is 200. And did I give me units for this? 200 meters. Because it was the velocity is given to me in meters per second, and I integrated it over an infinite number of seconds. So the value of my integral is 200 meters. So now part B asked me to explain what that value means. So what does that value mean? I got a unit for it, but what does that unit mean? Basically what that means is this. From the time this particle started moving, it is going to move 200 meters basically from now until the end of time, until from now on, basically. That is how far it's going to move. Yeah, from now on, from now until the end of time. Infinity is a very strange thing. It's very hard to describe in words, but that's how far it's going to move if I let it just continue moving unimpeded. It's going to move 200 meters. All right, so that is all we have for checkpoint 15.